Now let's start the first part. Kitinat Taweesintananon will present the trial lecture. The title lecture he got exactly 2 weeks ago is Artificial Intelligence for Seismic Processing and Imaging, State of the Art and Outlook. Kit, the floor is yours.
Thank you. So today what I'm going to talk about is artificial intelligence and some application recently published, and I forecast some future application for seismic processing and imaging. So the outline of the talk start with introduction. I will give you a basic idea what artificial intelligence is. And then I will introduce you in case somebody don't have much background for seismic reflection method for subsurface imaging, and then data processing and imaging. And then I will go into showing some recent applications for AI or artificial intelligence for seismic processing, and then conclude the talk. So first, come to the definition of artificial intelligence. Artificial intelligence. So people call it AI, and it is the simulation of the human intelligence processed by machines. So AI is commonly referred to as just one component of the technology, such as machine learning or deep learning that people might have heard. So actually, there are 5 key components of the AI that try to simulate the human intelligence. First thing, human can learn, can make some reasoning, and do some problem solving, have perception ability, and then can understand language. So AI actually try to simulate this kind of components to behave like a human. But today, I think we will focus in machine learning as a start of the technology. What is machine learning? ML. So machine learning is the field of study that gives computers the ability to learn and to predict outcomes without being explicitly programmed. The key one is without explicitly programmed. So you don't need to do your own code like in C language or Python in very difficult form. You may feed with some sentence, something like that, and let this technology predict the outcome for you. And machine learning can play the role where the physics is not well understood or economically tractable. So machine learning is to derive some kind of models in terms of mathematical model or computational models that can extract knowledge or patterns for the data. And some term that you have heard about deep learning. Deep learning is a subset of machine learning that in very simple terms can be thought of as like automation of predictive analysis. So the method, how do the machine learning system work? So first, it ingests large amounts of label training data. So we need to train the data, tell what the data, how it should be performed and analyzed. Secondly, analyze the data for correlation patterns, and then finally use these patterns to make predictions about the future states. The key one is to make predictions. So machine learning is to make predictions without explicitly programmed. So there are mainly several types of machine learning algorithms. First, supervised learning. So you know the answer of the data, you know the input, you know the answer, and you feed that kind of label to train the system. But for unsupervised learning, that's another key one. And there are another two is semi-supervised learning and reinforcement learning. For unsupervised learning, you don't have a clear picture about the exact answer. So actually, the key that the key techniques that people are talking about is supervised and unsupervised. And for supervised learning,
then we will have a short break.
Techniques like classification, regression, or unsupervised clustering. But for deep learning, I will talk about it a little bit more. So first, I need to have you an idea what machine learning is doing, especially the technique called neural network. So for example, if we have a handwritten pieces of number on this board, and each pixel have some kind of amplitude level of how intense you draw the number on the board. Like if white color, it should be number 1. If it's black color, it should be 0 amplitude. And all the pixel on this board is can be the draw as the circle here in the first layer. So each layer, each point refer to 1 pixel in the board here. And then we can form neural network by have like 2 hidden layer, and then try to connect how the pattern in the handwritten pieces here can predict as the exact number in the computation. So let's try what to get some sense what this can do. See if I can bring up some. So this one, for example, if you draw something, number 4, you see that they calculate something and then try to predict the good weighting parameter and some bias, try to predict for that. But this one is not look like it's correct. Maybe we need some pre-processing to form, to move it and to shape it a little bit denoise, and then you got the correct answer. So if you change some this one, the weight number within this layer is changed, and you get some. So it's maybe it's incorrect here. So that the glance. So neural network, which parameters are computed. First layer, I said activation here. You have a amplitude of each pixel when you draw, and all of the element in the layer 0 need to be computed to give the elements in the layer 1. For example, this one is amplitude in the layer 1 element here is a sigmoid function, is this kind of try to normalize the amplitude to be between 1 and 0, something like that. And then you have weight. Weight is kind of how much you need this information to transfer to the next layer. And also you have bias. So we can form that kind of thing as a matrix. Like you have you need to compute amplitude of each element in layer 1. So this kind of a vector, and then it's equal to we can write into this form. The problem is that we need to find the model by do some inversion to determine what weight and bias parameter should be. And then after we train the data to determine the weight and bias parameters already, we have a system that we can predict the result based on our drawing number on the board. So that's the concept. So it's kind of the same thing as inversion. So we need to try to determine weight parameter and bias. So next, move forward to the seismic method for subsurface imaging. So the seismic exploration, normally we have inject or propagate the wave or seismic wave from the surface. For example, we have a seismic source here. We propagate the wave down into the earth, and at some high velocity contrast, there is some reflection of the wave back to the surface, and we have seismic receiver deployed on the surface. And that on the right panel shows some animation where you try to simulate the what happened in the field. You propagate the wave, and this the bottom panel is what the seismic profile or recording profile that the surface receiver can show on the computer screen. So where the vertical time is time axis. So in the field, we have several seismic sources, and we shoot several times where we deploy the seismic receiver in the field. And then we have several seismic shot profiles. Then we bring that together, try to process it, and produce the subsurface image like this. And that you can think of a lot of application, like for petroleum exploration or for subsurface exploration. So let's talk about seismic processing. What is it? So as when we record the data in the field, we have several short seismic gather like this. We pass through the process called seismic processing and imaging, try to produce the seismic image of the subsurface of the Earth like this. So it requires a lot of work and integrate a lot of subjects, such as physics, geology, mathematics. You need some technology that in the modern day, you need the computer, you need a lot of computation things to process it, and it requires art and creativity from the person who try to determine the parameters for seismic processing. So let's talk about some terminology. For this shows some geometry of marine seismic acquisition, where you told the seismic source behind the vessel, and that same vessel told the streamer that record the pressure wave or it's the hydrophone told behind the vessel also. So when have air gun show here, and the next shot, the vessel move and air gun shooting in the next position. But in the shot record, we call common shot gather, because when we display normally, we display all the receiver from the same shot. But sometimes we can sort the data itself to the common midpoint gather or common depth point gather. That for example, we select only the red part or red receiver data to show on the screen, and we call it a common midpoint gather or CMP gather or something like that. So this is a simplified seismic processing step. First, I show this just one shot gather. You will have like direct wave event as a linear, and you have a seafloor reflection and some sedimentary reflection. And then what we need to do first is to attenuate noise that we don't need. Because it is seismic reflection processing, we will keep only reflection to build the seismic image. So we attenuate noise by maybe we edit noisy trace, replace with some interpolated trace. We correct amplitude for energy loss at distance for long travel time. For example, it's a spherical divergence that you might know, amplitude decay with the distance. We need to correct that to have a good image for the deeper part of the subsurface. And then we sort it to CMP gather, or it's called CDP gather sometimes. So we select some thread and sort it to CMP gather. And then we remove direct wave. We correct travel time of the offset dependent delay. you might have heard about normal move out correction or migration that try to correct the travel time as if the output seismic trace have source and receiver at the same location. It's like a zero offset trace. And some are traced together to have a high signal to noise ratio and then compress wavelet, and then you can do some migration or display for the interpreter to interpret the subsurface structure. So the seismic migration is a key processing step. Is try to correct the positioning of the dipping reflectors. For example, this is a true model of the Earth. The final goal is we want to produce zero offset image. So I illustrate here is shot and receiver at the same place. It's clear that the gray part for this fault plane is need to be this deep because it's need to perpendicular to the reflector. When we have this kind of structure, what happened in the data domain in the time distance plot? So because the vertical axis is time domain, you plot the data that you receive at this receiver vertically, and then at the time that the wave spent from this source to the reflector and back to receiver. So we plot like this, and if we plot the several receiver recording trace, is the fault plane reflection will be appear like this, have a shallow, low dipping structure on the data domain. So the key concept is to do migration. The migration is to migrate the data into the correct image position. So you need to go back into that image. So for example, the top panel on the right here is the data domain, is zero offset data. And you will see that there's some noisy thing. It's not the real structure of geology. So you need some migration to create a correct image before you can drill the well or explore more the subsurface structure. In short, simply gather through a conventional 3D land seismic stack depth migration processing sequence is like this. This shows just a few steps. First, you have the seismic raw seismic data, and this one I think already do normal move out correction, which is a time delay correction. Try to flatten some reflection event already, and then you do some denoise, remove noise, some linear noise, and you have some interpolation, missing traces, do some migration, and then you do some cosmetic to make to enhance the seismic reflector before stacking. So you can see that it starts from very complicated and very noisy data, but it's turned out to be you need some mathematical tool or computational tool in seismic processing to get the final product. This is a sample of a full seismic processing sequence in 3D marines pre-stack time migration. It looks like there are a lot of steps, and yes, it is. At every step, you need to, normally we need to determine the best parameter for each step. That means you need to do some parameter testing for each technique. For example, denoise or something like that, you need to set some good parameter for different areas. That take time. So it can be grouped in different main steps like reformatting, pre-processing to denoise or some trace editing, and do some migration, preparation, do real migration, and do some residual correction of the time after migration, and do some cosmetic to enhance the image. Traditionally, these all steps, including parameter testing, require 4 to 6 months for about 1,000 square kilometer area for marine seismic data, which take time and require human intervention. So seismic imaging, what is it? It is a method that estimates the subsurface models quantitatively. It is usually referred to as seismic migration. Objectives of seismic imaging. The first one is to estimate seismic velocity used in seismic migration. So seismic velocity modeling or seismic migration is kind of a mixed term for seismic imaging. So we need to produce a good velocity to produce a good migrated image. The second objective, you need to produce subsurface structure image and deliver image that can be interpretable amplitudes and other attributes that connect to rock and fluid properties. So we need to care not only the travel time, also we need to care about the amplitude. The two mechanisms is the first is to focusing, to collapse the diffractor, try to produce a good wavelet color background for the final seismic image. The second mechanism for seismic imaging is to position, try to correct the position of the seismic reflection. So this is, for example, the true synthetic model here. And first, if you want to have data, we can try to simulate the real seismic survey by doing data modeling to get some kind of this image, zero offset data, by using some wave propagate, some operator G, try to propagate the wave into the model and get the data here. Seismic imaging is try to return back to the image domain or kind of something look like the subsurface structure by applying some what that we normally call adjoint operator of G to the data and try to get the interpretable seismic image. But what inversion does is really try to compute the inversion metrics for the data in order to get the model. So this is the inversion. So that's a kind of difference between imaging and inversion in some sense. So now we see how we can combine artificial intelligence and seismic processing and imaging. The challenges in modern seismic processing is about the data size. Increasing the data size from the past to the current day plotted in this figure. So the vertical axis is number of traces per square kilometer, number of seismic traces per square kilometers when we acquire the data inland seismic, something like that. So at the like 1950, we start to do 2D seismic survey. We have very small number of traces per square kilometer. But nowadays we have capability to process and acquire larger 3D and denser 3D seismic survey. Now, and it recently achieved 1 billion traces per square kilometer for land. So it's quite huge number. If you think that one seismic trace generates 3,000 time samples, that means it's, and each sample is about 4 bytes. So you can calculate, and it's very huge number for each shot or the data set. So that means it requires more efforts in parameter testing and quality control because we have limited manpowers and computational tool. So you need a lot of effort in doing parameter testing and do quality control of to optimize the seismic processing within a short turnaround. So this is also the key, that you need to do everything within a short turnaround. For example, in petroleum exploration, you will be assigned a short time frame for exploration. Within 3 years or 4 years, you need to propose the well or need to drill the well. So you need to process it fast. But as you have a lot of data, you need to have a lot of computational power, or you need to have some good strategy to process it. What are the solutions? So the goal is to reduce the turnaround time while processing larger data set. But we need to maintain the quality and confidence levels in the output products. So the proposed solution is to progress to the full automation of the seismic processing. How? By minimizing the parameter testing, or by accelerating the quality control process, or try to automating velocity modeling. And here, when I talk about velocity, it doesn't mean only the seismic velocity. I also means any parameter governing the wave equation or wave propagation. Machine learning comes into our focus because it can help to predict some pattern and help human to design something, or try to help automation of the full processing work. So here, summarize some key technique in machine learning that I have seen nowadays in geophysics. But the key one for seismic processing probably is about the neural network, or some semi-supervised technique like unsupervised pre-trained network and neural network to denoise, remove the seismic noise and improve migration. So first, review some recent publications about the deep learning. So in 2020, there's some publication in first break showing some post-stack noise attenuation using deep learning. So let's see some result. You have input data, it is the stack data, and you want to denoise, remove the migration noise or the swing like this, which is artificial. It's not the real seismic, it's not the real geologic structure, you can see. So they put into train the data, and then train the evolutional neural network, and then they denoise the data using that network and get some good result. Compared to the conventional noise removal technique on the right panel, you can see that it's very impressive that its noise disappear from the image already compared to conventional denoise data technique. And also you can see some artifacts remaining in the conventional denoise data here, but you don't see it in deep learning result. It's really impressive. But first, what is the noise in marine seismic data? There are several noise. I read some example in marine seismic data. We have swell. What is the swell noise look like? This is before the noise. You have some high amplitude trace like this. And this is after the noise using some conventional method. You can see clearly what is swell interfere and contaminate in the raw data. Another type is clearly shown here is the seismic interference noise here. And if you look at the raw data, input data before the noise, you see that it interferes with the seismic reflection. And after the noise cleaner, and this is the difference between before and after seismic interference denoise. So that we need to have a tool to automate the denoising process. So this show in 2022 some publication in geophysics showing some seismic deep blending technique try to remove the seismic interference noise, and this just show the stack image. It is CMP stack image. Running this is the before deep blending, and you see a lot of things that is noisy. You don't see clear the subsurface structure. And when the deep blend using the proposed deep learning method is come here, and it's quite nice. And if the deep blend stack using conventional algorithm is look like this bottom figure. So they try to compare, and the runtime for such as machine learning or about 5.5 hours for training, and then it's very short time, just less than 1 second for applying deep blending for one shot gather. So the majority time is for training. And for the runtime of the conventional method is about 2 times of the deep learning runtime, include training. So that we see some opportunity that if we have a very nice deep learning model, we can reduce human time and processing time, as you can see here. Another idea is to automate the QC using supervised classification or some supervised learning. They try, because we have a lot of data nowadays, we cannot try, it's quite impossible in short time that we need to look into every shot gather on the computer. So to save time of quality control, we need to generate attributes. We move from the data domain to attribute domain. For example, we compute one shot gather will return to be maybe just 1D attribute. So we reduce 2D shot gather display into just 1D amplitude attribute, something like that, and that reduce the number of time and the effort we need to QC the data. So we use that idea, the paper in 2019, use that idea, try to generate an attribute and try to develop some machine learning system, try to detect and determine which parameter, for example, should we apply very harsh parameter for denoise, or we apply very mild parameter for denoise. So they developed that kind of system, try to answer that automatically. Don't need to wait for the human to decide which parameter should it be. So it's so save time. That I grabbed some image from that paper. They try to compute different kind of attribute and try to plot it and try to classify the which one give the accepted result. For example, they can determine some denoise technique, like this parameter provide in general good result, acceptable result as green color, but maybe you have something that not acceptable in the red color or blue here, like, and then they show that yes, exactly, they have some remaining or residual thing in the data that we cannot remove it by this, something like that. So this it helped in the QC. So the third one is about velocity modeling. So we need, final goal is try to automate the velocity model building process. So this shows you some result of tomography, travel time tomography. This is a model fitting method. And the result shows this traditional method give quite low resolution in the subsurface velocity model. Compared to the modern technique like full waveform inversion or FWI, which is a seismic data fitting method. You try to find and minimize the data residual to produce high resolution velocity. So we move forward to this technique, but this technique requires a lot of computational power. So briefly about FWI, it is the way to find the velocity model by minimizing the misfit function. The misfit function here is the difference between observed data and the modeled seismic data. So I try to optimize in least square sense. And we need to find the updated model. We have initial model, we find updated model by computing. First thing is to compute the gradient of the misfit function, which and the inverse of the Hessian matrix. The technique is just try to compute data residual, compute the gradient, and step length is the representation of the inverse Hessian matrix, and then try to update the velocity model until we find the good velocity model. The key success of the FWI is to determine the accurate source wavelet, field data with proper preconditioning. We need to have good initial velocity model, reliable algorithm, and comprehensive QC to ensure that we don't have cycle skipping and we have good migration result. What is cycle skipping? Normally, we, for example, the field data is the yellow, but the model data is the blue line here. You can see it's not aligned well. The traditional cost function for FWI is to subtract the data, observed data, and model data. And you can see that if the data is, if model data is have travel time different more than half wavelength, it's have problem to behave like a human. And cycle skipping give you to local minima, and that means your solution is wrong. We need to move to the global minima. So we need low frequency component to avoid the cycle skipping effect here. So in 2020, the published in Geophysics proposed some technique to extrapolate low frequency model seismic data using deep learning. So it helped FWI to determine the velocity without the problem of cycle skipping. So for example, quickly, this is FWI result from band limited data without low frequency. So this is FWI from the low frequency extrapolated data using deep learning. And this is the FWI from the full band data. You compare this and A and B, you can see that B give more reasonable data, velocity model, especially in this zone, where if you miss the low frequency data, you will not get the good velocity model here. Another paper recently in 2023 tried to use deep learning UNet network to try to help FWI to build the model for salt body. This is a kind of idea of UNet architecture. They contain a lot of convolution neural network, and have some criteria between passing from the current layer to the next layer, and then before outputting the prediction. And they have some three successive unit network by different purpose for solve flooding, and then starting from scratch, it's like this one, and then on the right, they try to evolve, update the velocity model using this kind of technique, and it's quite promising at the end here compared to the true model here. But there is some way to go in terms of research and development. So the goal into the outlook now, the goal is to reduce the turnaround time by processing the larger data set and improve the quality, or at least maintain the quality and confidence level in the output product. So AI, artificial intelligence, and machine learning can help us and accelerate to step closer to the full automation of seismic processing by these three procedure: minimizing the parameter testing, try to help and reduce human bias in quality control, try to automate velocity modeling. Conclusion: machine learning is a component of AI. Several studies have shown some advantages of machine learning in seismic processing and imaging toward the full automation of the work. Soon, we should expect to see more machine learning applications and some of their case studies, especially on the term of automatic parameter testing, automatic QC, and automatic velocity model building and imaging. And that comes to the end of this lecture. And thank you. And if you have any questions, just let me know.
Thank you, Kit, for this lecture. I will turn to the first opponent and to see if he has questions.
Thank you for this lecture. In your conclusion, you talk a lot about speed up and automation.
Yes.
Did you see in your literature review, or do you have any idea of things where AI could bring something that we cannot do with current tools? Like just not, make things faster, but also be able to do things which were difficult or tricky to do otherwise.
I think currently we try to replace the step that we can do by machine learning. I haven't seen much publications about try to do totally a new thing. But because currently processing seismic sequence is there are several seismic processing steps that we can do already. We just need something faster. So that
okay.
Because I haven't seen much publication about that innovation, just totally new thing with AI. No, I haven't seen much.
Maybe a more specific question on slide 25.
Yeah.
Here you put a lot of stress on this approach.
Yeah.
And I didn't get why the other ones didn't seem as important.
Yeah, because this talk is about seismic processing and imaging, so I see much about this one in this term. But as I show in some example, for example, to help human QC the data, they use supervised learning classifier. Yes, in this So it does not limit to only deep learning, but I saw many people working into the seismic processing techniques, or they use a lot of deep learning. But yeah, some minor paper, yeah, they talk about helping the people how to QC or make a good decision. They use supervised learning.
Okay, so it's not like we know that the one you highlight in red is better. It's just that there is more work focused on this kind of approaches right now.
Right.
Yes. Okay. To some questions or. Yeah.
I think before asking him, I don't know much about AI, so you taught me a lot already. And I think also, by the way, your presentation is supposed to be a pedagogical presentation. So I think you started very well, and then more towards the end, you were more technical, right? So I'm not sure it's always easy to follow. But what I can see, we had a similar lecture with another candidate in Bergen, and you did much better than this candidate.
Thank you.
You did explain much better at the start of the presentation. But again, this AI is really into helping avoiding the cost of doing the processing, avoiding also the bias of the processors, because I guess there's a lot of bias. People who have been processing for
this
same kind of data, then they choose the parameters without even thinking outside. So I think, maybe, would you say that the machine learning is going to give us more standardized or more unbiased images, that there's a lot of human biases in the data we have per today?
Yes, I guess so. That because currently different oil company or different seismic processing service company have their own character. Like it depends. Each seismic processing project totally depends on the person who make the decision about the parameter. That's why you will see a lot of projects need to do some reprocessing, because new people have something in their mind and they don't think that the what people did in the past is correct or is good enough, so they want to have their own decision. So I think AI is kind of maybe help in terms of reducing human bias.
It's more neutral in a way, that because you did mention also cosmetics, right? We always have the feeling that in seismic processing imaging, there's some cooking recipes. You want to have this out, so you do some tricks here and there, and then so maybe AI will try to avoid these kind of things. But you had, I don't remember now, I didn't put the slide number, but you said at some point we had very nice denoising of a seismic section, and you say, oh, this is nice. See, but what if this stuff which has been removed is actually maybe more the small details, diffractions? It looks nice, it looks smoother, but is it better? Maybe there's still some, how the machine is going to make the difference there.
Like this one?
Yeah, because I think you may have removed then more diffraction information.
Because I think currently we don't have standard that people have the same agreement, which this image is better than the noisy image or not. Because in the past, maybe 10 years ago, people prefer to have quite clean, really clean data image. Is to have kind of
smooth,
high coherency, strong coherency in the same reflector. But I think the current trend recently, we try to have more detail of the diffraction point. Of we don't want really clean or continuity of the reflector. We want some more detail in this, for example, detail in here maybe is the true data, true image, true geologic feature. Yeah. So we still need to have some standard that compromise.
So we still need the human being, right?
Human being. So this kind of bias done by
Because an interpreter would say, oh, this is nice, I can better interpret this section, but it doesn't mean that the information was,
Maybe you lose some real feature. For example, maybe there is real fault here. For example, in this pointer. And if you want, we need to determine the good model for neural network.
And I think there's quite a lot of activity in AI for diffraction, actually, right? Diffraction detection and diffraction imaging. Okay, but I think you did very good for the lecture.
Further question?
Any question?
I will maybe ask one question. So you mentioned that these machine learning techniques require a lot of data. Is that always compatible with the standard way of carrying out seismic surveys? And in return, is there any evolution in the way seismic surveys are carried out, considering that the intention is to use deep learning or tools that are data intensive?
You mean, I think the trend of seismic acquisition will generate more and denser data set. That means more data. But the question is about the.
Put differently, if you take the result of a classical seismic survey, you have enough data to train a neural network in a proper way.
Yeah, because maybe a neural network doesn't need to be trained by one data set. You can have a lot of data set from different survey areas until you get the good model network for that. But I am not quite sure I understand your question.
I think you answered properly. Okay. So that's all for myself. So thank you very much for the lecture and the discussion. And this first part of the defense is closed. And we will resume the defense at 1:15 this afternoon.